Hello friends, finally today I'm going to complete this paper, Quantum Mechanics and Application of BSc 5th SEM paper, Dibrugarh University, 2021, held in January and February 22. So this is for physics honors, BSc physics honors students, C-11 paper, Dibrugarh University. This is under Dibrugarh University. Okay, so in question number in part 5 we have solved up to question number 12. So today we're gonna start from question number 13, right? So we're gonna complete this paper today, and I have taken a long break. I have taken long time to complete this paper, so I have already made 5 parts, and links will be given in the description box. And before we start, please subscribe the channel if you are new to my channel, and also share with your friends if you think that my videos are helpful. And I'm gonna try to solve question papers of other universities also, like Guwahati University or any other universities. Okay, just I need time. So now let's start today's video. Okay, that is 6th part. So let's start from question number 13. So in this question we are going to discuss about LS coupling. Okay, so this is the answer, right? So what do you mean by LS coupling? Now you see, before we discuss about LS coupling, so let me tell you about an atom single in case of single electron atoms. Now you see, this is the nucleus. Suppose an electron is revolving around the nucleus. So what happens here, this this electron will revolve around this nucleus, because of which it must have you know orbital angular momentum, and it will spin as well, because of which it gonna have uh, spin angular momentum. There are two types of momentum, one is spin angular and another is orbital angular momentum, and combining these two we're gonna get another new kind of momentum, that is total angular momentum. And this combination is called actually coupling. Now you see, in case of multi-electron system, now suppose you have an atom, and this is the nucleus, and suppose there are 2 electrons in its outermost shell. Then what will happen? So here you see how to get the you know how to get the total angular momentum in this case. Okay, so this in this case, its individual electron will have uh, orbital angular momentum and spin angular momentum. So suppose L1 and S1. So similarly it gonna have L2 and S2, suppose spin angular momentum and orbital angular momentum. So here you see, it can combine 2 ways. One is like this, that orbital angular momentum of this electron and orbital angular momentum of this electron, combining the orbital angular momentums, it can give resultant angular momentum, suppose L, capital L. Similarly S1, combining S1 and S2, that means spin angular momentum of 2 electrons can give combination of these two gives a resultant spin angular momentum, that is suppose capital F. Then combining these two, resultant L and resultant S, combining these two can give the total angular momentum, that is capital J. So this type of coupling is called LS coupling, right? So let me explain it properly. Now you see, we have angular momentum L1, L2, L3, etc. of electrons. Okay, so then spin angular momentums S1, S2, S3 in a atom. Okay, multi-electron atom. Then what happens? We used to add the orbital angular momentums vectorially, added to produce the total orbital angular momentum L. And similarly these are also added to or combined to these are also combined vectorially to form total spin angular momentum S. and using symbol we can write this way. This is the resultant orbital angular momentum. We get it by vector addition of individual and angular momentum, orbital angular momentum of individual atoms, that is summation Li. So similarly we get resultant S as well. Then final results, that resultant L and S, combining these two we get the total angular momentum. So this is nothing but LS coupling, right? So now you see, let me go to the next slide. Here you can see, so these are the I have written here what does L, S and Z represents here. So the values of L which are allowed are this, from L is equal to L1 plus L2, then L1 plus L2 minus 1 dot 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 modulus of L1 minus L2. So now you see, if we have now you see two orbital angular momentum of quantum numbers L1 and L2 combine to form L, capital L, then the allowed values of L are this, right? Similarly we will get allowed values of J, this, after getting resultant L and S. So values of J starts from capital L plus S, then L plus S minus 1 and so on, then mod of L minus S, right? Now you see, when L is greater than S, then you can say S plus 1 values for J, and when L is less than S, then possible values of J, that is given by del capital L plus 1, and this 2S plus 1 is known as multiplicity of multiplicity of the state, right? So now you see, so what do you mean by multiplicity state? That means you see, if you get the value of right, if you get this value 2S plus 1 is equal to, suppose 4S, suppose S is equal to 0, 4S is equal to 0, if you get you will get 1, this value is equal to 1, that means it's gonna represent singlet, okay? Then if you get multiplicity 3, then it's gonna be triplet, like that. You see, if you consider the case of simplest multi-electron system, that is 2-electron system, for which you will get 2 spin angular quantum number, that is half S1 and S2 is also half. Then values of S will be given that will be allowed from S1 plus S2 to S1 minus S2. That means here S1 plus S2, that gonna half plus half, that gonna be half plus half, that's gonna be 1 to 0, right? So here we're gonna get only 1 and 0, value of S we're gonna get 1 and 0, right? We are going to get 1 and 0. So in that case, for S is equal to 0, you will get 2S plus 1, that's gonna be 2 into 0 plus 1, that's gonna be 0, sorry, not 0, 1, that is that represent singlet states. And S is equal to, for S is equal to 1, you're gonna get twice, it implies 2 plus twice S plus 1, that's gonna give you 2 into 1 plus 1, that's gonna be 3, that is triplet states, right? So hope you have understood. So now you see, the state symbol is represented by this. Here n is the principal quantum number, and this value of L gives its S, P, D, etc., representing the orbital angular momentum quantum number, right? Orbital angular momentum quantum number. And this 2S plus 1, that gives the represents the multiplicity of state, and here J is the, this is J represents the total angular momentum quantum number, right? So these things, hope you have understood this. Now this is the selection rule for LS coupling scheme, right? So now you see, the aim of this video is to provide you the answers, solutions of the question paper, okay? So I'm not gonna explain in details everything, so let's move on to next question. Okay, so without wasting time, let me show you the next question. So now, how can we this is question number 14. How can the states of an atom be represented in spectral notation? So this is how we can represent spectral notation of atomic state or states of an atom, right? So here this n 2s plus 1 l j. So here n represents principal quantum number. That means it's gonna be k cell, l cell. So that's gonna give you that's gonna be given by this principal quantum number, right? And this l, the value of l, if l is equal to 0, then it means s, and if it is 1, then that's gonna be p, and if 2, then d. So it's gonna give you the orbital angular momentum quantum number, right? And here j is the total angular momentum quantum number. So now let me consider the case of 2 electron system for which small s1 and s2 that's gonna be half, right? So in that case, value of s will be will be given by from s1 minus s2 to s1 plus s2. So that's gonna be from 0 to 1, half minus half 0, and half plus half 1. 0 to 1 only we will get two values, that is 0 and 1. And in that case, so what gonna be the now you see here, so what will be the multiplicity state here you see. So for s is equal to 0, and that twice s plus 1, that is the multiplicity, right? So it's gonna give you 2 into 0 plus 1, that's gonna be 1. That will represent singlet, okay? So and for s is equal to 1, value of this s 2s plus 1, that's gonna be 2s plus 1 gonna be 3. That's gonna represent triplet, right? Now you see, let me clean these things. Now you see, suppose we have value of s is half, right? S is equal to half, L is equal to 1, right? So if L is equal to 1, that means it's gonna be P, right? Here you see, for S, if L value of L is 1, if the value of L is 1, value of S is half, then what will be the value of J? That's gonna be given by L plus S, right? Value of that J is given by that I have already shown you, that given by L plus S, then L plus S minus 1, and so on, then L minus S, right? So here you can see, if you take L plus S, that means 1 plus half, then it's gonna be 3 by 2, right? And then L plus S minus 1, that means 3 by 2 minus 1, that's gonna be half, right? And if you take L minus S here, if you see, again L is here 1, S is half, so that's going to be half. That means this L plus S minus 1 in this case is the last value here, L minus 1. That means because we are getting the same, right? Here also half, here also half. So we have got two values, one is 3 by 2 and another is half, right? Another is half. So here we have got two values of j, that is 3 by 2 and half. So what will be the notation? Let me clean this part. So let me tell you what should be the notation. So I have told you that notation is given by, this is n is principal quantum number, so ignore it for the time being. So 2s plus 1 l j. So for this value of l, so this should be replaced by p for l is equal to 1. If there is l is equal to 0, then this should be replaced by s, right? Then for value of s, which is half, right? So if you put here half, then it's gonna be 2, right? And value of j, we have got 3 by 2, so here 3 by 2, and we're gonna get here double it, so we have got two values of j, that is another is 2p half, right? So this is double it, right? Similarly, you can explain this also. For s is equal to 1, l is equal to 1, you will gonna get these values of j. J will be equal to, you say l plus s, that's gonna be 1 plus 1, that's just 2, and l plus s minus 1, that means 2 minus 1, that's gonna be 1, and then l minus s, that is 1 minus 1, that's gonna be 0. So you're gonna get these three values, right? So for these three values, you're gonna get triplet. So as we are taking here also l, so that's why you're gonna get p, here also p, here also p. So and twice s plus 1, as we are taking value of s is 1, so you will get s 2 into 1 plus 1, that's gonna be 3. So multiplicity of state is here 3. So then in that case, let me clean these things. So here you see, so as we have got multiplicity state is 3, so and we are taking l is equal to 1 here, so 3p, and we have got j is equal to 2, 3p2, then we also have got the value of j is 1 here, so 3p1, and another is we have got 0 also, so 3p0. This is triplet, right? So hope you have understood these things and how we can represent the state of an atom or with the help of spectral notation of states of atom, right? So hope you have understood this. Now let's move on to the next question. You can solve this question or the next one. The next one is this. So here is the last question of this paper. What is meant by the fine structure of spectral lines? So let me write here the meaning of that. So this is the answer. The fine structure of spectral lines is the splitting of main spectral lines of an atom into two or more components, each representing a slight different wavelength, right? Suppose let me take an example. Suppose transition is taking place from an s orbital to 3p orbital, suppose, right? This is the main spectral lines, right? So now you see, due to spin orbit coupling, okay, so we will get 2 or 3 components of this line, maybe 2 or 3. So we're going to discuss it later, and these fine components are nothing but fine structure of spectral lines. So let me explain in details. You will understand these things when I'm going to explain about this next part of the question. Describe how spin orbit coupling explains the fine structure of alkaline spectra. So let's discuss. In alkaline spectra, we get 4 series: surf series, principal series, diffuse series, and fundamental series, right? And transition takes place from in surf series from ns to 3p, np to 3s. In diffuse series, in principal series, we get transition from np to 3s. Then in diffuse series, we get from nd to 3p, and in fundamental series, nf to 3. right? So now you see n, in this case n is from 4, 5, 6, so on. Let me show you how. So when you write electronic configuration, first you write 1s, then 2s, 2p, and so on, right? 2s, 2p, 3s, 3p, 3d, right? Then 4s, 4p, 4d, 4f. In this direction, energy level, is going higher, right? Now you see here ns, from ns to 3p, this should be the higher energy level. So as here you can see, so compared to 3p, 3s is lower in energy level, so that's why we're going to take the value of n, which is before s, is 4, because 4s is higher than 3p, right? So that's how we proceed. So here you can see np to 3s. Here we can take from 3, so you may think that here we have taken when there was 3 before p, we have taken the value of n is equal to 4, but here we have 3 already, but why should we take 3 here before p? Because you see 3s, right, and this is 3p. 3p is higher than 3s. So hope you have understood this region. So now you see let me explain those things, fine structure of alkaline spectra with the help of spin orbit coupling, right? And spin orbit coupling gives a total angular momentum of atom. Its magnitude is given by mod of j, which is equal to root over small j into small j plus 1 h cut, right? Where this small j is the total angular momentum quantum number, right? And once you get j, then this value gives a multiplicity, that means atomic states, right? How to find that multiplicity? That atomic states or multiplicity is given by j is equal to, not j is equal to 2j plus 1. This is gonna give you the multiplicity, right, or atomic states. Now how to get j? In order to get j, we must know spin angular momentum and orbital angular momentum, because due to spin and orbit interaction of spin and orbital angular momentum, we get total angular momentum of atom, right? So spin angular momentum, that is capital S vector, and its magnitude is equal to root over small s into small s plus 1 h cut, right? And where small s is spin orbit spin angular momentum quantum number, right? Now orbital spin angular momentum number. Now let us discuss about orbital angular quantum number. So orbital angular momentum, that is represented by capital L vector, and its magnitude is equal to root over small l into small l plus 1 h cut, and where L is the orbital angular momentum quantum number. So pause the video and take the note. Okay, so now let me go to next slide. So once you get small s and l, right, then small j will be given by l minus s to l plus s, right? And and the selection rule that we're gonna follow here, that is del l is equal to plus minus 1, and del j, that's gonna be 0 and plus minus 1, right? And here you see, for all electrons, in alkali metals there is only one electron in outermost cell, that means which is optical electron, and for one electron the value of small s is always half, right? So, and this spin angular momentum, total spin angular momentum for paired electrons is 0. Remember that. That means if there are two electrons, then its value will be plus half, and that of value of small s for the other electron will be minus half, and plus half minus half, total 0. Right? Hope you have understood this. Now let us discuss about the force series. So how do we get triplet, doublet, right? Now you see 4 and S. For in alkali spectra, in alkali metal, so there is only one electron in outermost cell, that is, and for each electron, and the value of small s is half, and for s orbit, that value of L, small l, is 0, and value of J in this case will be half. It doesn't matter if you add L minus S or L plus S, you're gonna get same value here in this case, in this particular case. And if you represent this in spectral notation that we have already discussed about 2s plus 1 L J, so in this case, so value of S is half, so if you put here half, then you're gonna get 2, right? And in this case L, for here you see this is S orbit, so we can write S here, and value of J we have got half, right? So this is 2 as half, so it is single energy level. So here you see for 3p, the higher energy level. So for 3p, we're gonna get again s is equal to small s is equal to half, but in this case L will be equal to 1. For p orbital, small l is 1, and value of J we're gonna get L minus s, and L minus s to L plus s divided by 1 unit, and that's gonna be half if you subtract, and if you add, then you're gonna get 3 by 2, right? And in case of spectral notation, then we can represent this p orbital. So if you use the spectral notation, that 2s plus 1 here L J, so then you're gonna get if you put here half, s equal to half, that's gonna be 2p, you will get half, and 2p 3 by 2, right? So this higher one is 2p 3 by 2, and the lower one is 2p 1 by 2, and this is nothing but 3p, right? So here you see this is main spectral line from ns to 3p will be split into doublet like this, right? So here we have got doublet. This one is split into two spectral lines, right? Splitting into two spectral lines. Right. So this is called doublet. Right. So hope you have understood this. And what selection rule we have followed here, that L, that's going to be plus minus 1. So here you see S and P. For S and P, the value of L is respectively 0 and 1, and difference between 0 and 1 is either plus 1 or minus 1. If you take 0 minus 1, that's going to be minus 1, and if you take 1 minus 0, then going to be plus 1, right? So here we are taking s orbital, right? Its value is 0, and here it is 3p, so 0 minus 1, that's going to be minus 1. So we are obeying this rule, and del z, that's going to be plus either 0 or plus minus 1, right? So if you see how to find del z, subtract this half and this value, that's going to be, if you subtract half from 3 by 2, you're going to get 1, and if you subtract half from half, you're going to get 0, right? And for both values, the transition is possible. So here we have got two spectral lines, fine structure, right? So this is doublet. This is about sharp series. Now let's go to next series. You can see for this series, principal series, so values of small s, small z, small l are already I have written here, and with spectral notations for this orbital. And for this 3s orbital, this is higher energy level in this transition from p to s, np to 3s, where value of n are those, right? And this is a small s, l, and z, and these are the spectral notations. Here you can see in this case the main spectral line from np to 3s will be split into doublet. That means if you obey this selection rule, del l, that's going to be plus minus 1, and del small z, that's going to be 0 and plus minus 1. So here you're going to get two fine spectral lines, right? And we used to call doublet. Again we are getting doublet here. So this is the main spectral line. It is splitted into these two doublets, right? So hope you have understood this. Now let's go to next series. So for diffuse series, these are the values of higher and lower energy levels. For nd, these are the values, and for 3p, these are the values. And here this main spectral line from nd to 3p, where values of n are those, will be split into three spectral lines that we're going to say triplet, right? Let me show you this one and this one and this one. So we must obey this rule, selection rule, del l plus minus 1 and del small z, that's going to be 0 or plus minus 1. So here you see this spectral line, let me draw in blue, from this orbital to this orbital. This is not allowed here, because you see this is d5 by 2, right? And this is 2p half, 5 by 2 minus half, right? That's gonna be 4 by 2, that is equal to 2, which is neither plus 1 nor minus 1 nor 0, right? So that is why this blue line is not possible, right? Let me clean these things. So now let us go to the next and last series, that is fundamental series. So fundamental series, so this is the higher energy level, and we have got the corresponding values of s, l, and z, and this is the lower energy level, right? This is here transition takes place from nf to 3d, and these are the values of n. Here the single main spectral line get split into triplet, right? So one we're going to get from here, and from here to this orbital, and another from these two. So here we must obey this rule, selection rule is, so let me write the selection rule we have followed here. So that is del l is equal to plus minus 1, and del z, that's going to be 0 and plus minus 1, right? So we have to mention these things. So hope you have understood this. So if you think that this video is helpful, please share with your friends and hit the thumbs up button. Inspire me to create new contents for you. And if you have any question paper other than this, then you can send me via my email. Let me write the email, and please do subscribe that channel if you are new to my channel. So this is my email ID, Lakhyajit 123@gmail.com. So this is my ID. You can send your question paper, physics questions paper, via this email to me. So thank you for watching. See you in the next video.